It's a great pleasure to be here, and what I'm going to do is to give you an overview of several themes, then kind of several topics. When combined together, it creates a very nice and very natural kind of framework for doing Bayesian computing for what's called latent Gaussian models. So it's all about the class that models we consider called latent Gaussian models. They are kind of constructed from what's called Gaussian Markov random fields, and in a natural way. And if you mix this with numerical method for sparse matrices, which is extremely fast and efficient, and you do clever kind of what's called integrated classical Laplace approximations, this leads to some very nice results. So if you combine this in a correct way, this gives very nice approximation inference method, which is called INLA, which is what we find in near all cases are much faster and in practice much more accurate than essentially MCMC. So this is very, very, very promising. Just a disclaimer, just to say that this is not, I don't consider this approach, or we don't consider this approach to be not a rival, not a competitor, not a replacement for MCMC. It's just a kind of better option for this class of models. Okay. So the plan for this afternoon is that we have this first lecture, and then we have a break, and then a second one. And I want to say a little bit about the background on Bayesian computing, define the kind of the concept of latent Gaussian models. That it's not very surprising. And then talk a little bit about Gaussian Markov random fields, the importance of being Markov, and the importance of being Markov in the case where you're doing hierarchical models. And we'll talk about computational advantages using Gaussian Markov random fields. Look at these classical Laplace approximations, how we could build, and how we could kind of construct this approximation inference. After the break, we have a break in between. So after a break, we talk about a little bit about numerical method for sparse matrices. It's kind of useful to understand how they work, and of course, everything is kind of not surprising. Yeah, but the good thing is that we don't have to kind of code this up ourselves. You know. We'll discuss a little bit our INLA package. It's like a R package that kind of implement all these kind of things. I hope I have time to also discuss Gaussian fields, like Gaussian fields in 2 dimensions or even in dimension 1 that doesn't have Markov properties, but you can construct a representation that has. Okay, and then end with some discussion. So that's the plan. And the background for us studying here is that the issue of Bayesian computing is not solved, even though we have MCMC. Okay, and there are still problems with MCMC, even though the kind of we can compute with it much faster now than we could before, like 20 years ago. But still, it's not kind of this problem is not yet solved. Okay. The other thing that also comes to mind is that the models we're using today is much more kind of difficult than those that was around like 20 years ago. And especially this notion of hierarchical models, that you build models on using hierarchies. You know. This is very, very difficult for constructing sampling as well. And if you want to do Bayesian modeling, you have to tackle the Bayesian computing. And as it is now, the generic nice tools is JAGs. That's very nice re-implementation of essentially windbags. And also the nice new initiative called STAN by GLMM and friends. That is all based on MCMC. instead of kind of saying that, oh, wait, let's try to solve everything. Okay, maybe we can kind of consider a subclass of models that we can kind of tailor the kind of the inference algorithm for, and hopefully solve that class of model well. And if you don't have a model of this class, don't blame me. So it's this GLM, generalized linear model, generalized additive model, all these generalized linear mixed model, generalized additive mixed models, and generalized all these kind of that has something with general linear. It's all the same thing. And this kind of model, this class of model, is to put it all together. This is the most important class of statistical models. This is the most that have been. This is the class that is most used. So many kind of models that you see are not necessarily represented or kind of sold in that framework. It's just happened that they can be cast into that framework, and often without knowing. And there are kind of many papers kind of reinventing things that, oh, we can take this model and put it in that framework, and we can use that code to do the work. And for this class of models, even there is no kind of good enough solution around. And many of those kind of approaches doesn't scale well. Okay, scale well, we think that the dimension of this model kind of increase. We talk about, for us, is like a few hundred is a small model. 5,000-10,000 is a medium model. From that point up to 200,000-300,000 is a large model. Okay, so we want kind of model that kind of scale well on this scale as well. All this kind of, the Bayesian version of this generalized linear additive, all these kind of things, that is all the same thing. It's all kind of built upon using what's called a linear predictor. Okay, so it's a linear predictor is something that you kind of connects with your component, and it connects with the data. Okay, so the linear, you build up the linear predictor just as you do for the linear regression case. You might have a kind of intercept, mu is intercept. You might have what's called fixed effects. Okay, so we can use fixed effects and the phrase random effects because it makes the kind of language easier. But in the Bayesian context, it's all the same thing. Okay, it's just a different prior. So we might have some fixed effect with covariates defined in the matrix A, and we might have some random effects. Okay, and they are normal. We come from some covariance matrix with some parameters theta. Okay, and you can have some noise as well. And then we kind of connect this model to the observations. And we make the kind of tactical assumption already now that each observation only connects to one linear predictor. Okay, there are ways to extend this, but we'll discuss that later. And then we might have some what's called hyperparameters. Parameters kind of controlling the effects. So the parameters in the covariance matrices are usually kind of variances, precisions, correlation, over dispersions, and these kind of things. Here is a very simple example of what's going on. If you want to think about a smoothing binary time series. You have a time series of counts. It could be binary or some binomial distributed. So, and then you can say that there is a probability of like observing a success, a 1. It's a function of time. And what you want to do is kind of explain this, how this probability depending time, depending on the different covariates and so on. So what you do is you kind of link this probability to the linear predictor, and you kind of build a model for the linear predictor. Like you have an intercept, it's a beta times some other covariate c. That could be, for example, a different time series, possibly lagged behind. And there could be different kind of processes going in time, u and v. And u could be like an autoregressive process. We like these autoregressive processes because they are kind of Markov. So it's, and this autoregressive process has, let's say, two parameters, the correlation and the margin of variance. We could have another kind of process in time as well. It could be an unstructured term, like a classical kind of random effect. It could be a slow varying trend, something you can have two processes, one in on different time scales, and so on. And then, since we kind of, if we think about priors for these, we might use Gaussian priors for all this, the autoregressive processes, the intercept, and the fixed effects. And then, since we combine these kind of model components by just adding them together, and you have kind of Gaussian priors, you see that all this linear predictor itself will also be Gaussian if you condition on the hyperparameters. So we can kind of create this huge vector, it's called X, containing every component in the model except the hyperparameters. And condition on hyperparameters, this vector would be Gaussian. Okay. The hyperparameters here are like the correlation, the lag-1 correlation in the autoregressive processes, and the two variances in the time processes. Okay. So what's special about this vector X is that it's Gaussian and contains every component in the model, including the linear predictor. And it turned out that if you work out not the covariance matrix, but if you work out the inverse covariance matrix, this precision matrix, this vector is very, very sparse by construction. Okay, so this so you see the kind of sparsity pattern, and sparsity here connects to condition independence. Okay, so this vector has a lot of condition independence, but they're all kind of dependent. And sparsity here is a good thing because it allows for very, very, very quick computations. Okay. And we can kind of take this model and recast it into a more general framework. And this is how we define latent Gaussian models. So we have some parameters, theta, that comes from some prior. Condition on theta, you have a latent field that you don't observe, X, that is multivariate Gaussian, usually with some mean 0. And then condition on X, some of these X's are observed. And the linear predictor is part of X. So that's why it's kind of the linear predictor connects X to the data. Okay. So what's kind of characteristic here with this kind of setting here is the dimension of this latent field is usually large. Okay, so that's typical in order of 100 up to 100,000. And why is that? Because it contains a linear predictor, so you can easily have a few hundred if you have time series of a few hundred. Contains a linear predictor. It contains like the U process, one process in time. It contains another process in time. Okay, so there is easily a few times the length of the time series in this case. The other thing that is characteristic is that the dimension of what's called theta, the hyperparameters, is essentially those parameters that are not Gaussian is small. Okay, and they are typical like 1, 2, 3, 4, 5, this kind of dimension. And why is that? In this case here, you only have dimension 3. You have only had 3 hyperparameters. And this comes from that you have one kind of autoregressive component in the model, and that comes with kind of 2 unknown hyperparameters, the kind of lag-1 correlation and kind of a variance. And those 2 parameters are still 2, even though the length of this process is long. You know? So it doesn't scale with time. It only depends on being there or not. And then you have another term, this unstructured term, for example, or some smooth varying trend. It might only have also, just have kind of one hyperparameter, no matter of the length. So the number of hyperparameters essentially depends on the number of kind of model components you use to kind of build your model with. Okay. This model here is kind of our kind of target, and this is how we define the latent Gaussian model in this context. And this is extremely good for computation, but it's not any good for doing modeling. Okay? So if you have a problem at hand and you want to kind of, how should I do this? How should I model? How should I approach this kind of model? Starting to think in this framework here doesn't really help. Okay? If you have a model, very often you can cast your model into that framework, and if you then have some access to some nice general code that can attack this, then you can kind of do the computations in that framework. That's why we say it's good for computation and not for modeling itself. There are many examples that kind of you can throw into this framework, and from more the statistical point of view, this dynamic linear model, volatility model, all these GL things, measurement error models, kind of a little bit surprising, but they also kind of fit into that framework. All the stuff about spline smoothing, a lot about other kind of smoothing. Going more space varying regression model, all the models for disease mapping, log-Gaussian Cox processes like point processes driven by Gaussian processes. Model-based geostatistics, we're coming back to that later, with Gaussian fields and doing kriging, all this kind of stuff. You can also throw into this framework here. Space-time models, survival analysis, Cox proportional hazard models with time-varying frailty models. A lot of this can be thrown into this framework. Okay. Another thing that's important that we showed, like the precision matrix is extremely sparse. And this will kind of play a key role. And kind of Gaussian variables where the precision matrix is sparse is called Gauss mark-around field. That has close connection to kind of Gaussian graphical models. And they have two important benefits. The one is that it's a kind of natural tool to use when you have hierarchical models. You can think if you have a linear predictor, you can add a term, you can add a term, you can add another term, and this defines like the hierarchy. And this kind of plays so nice with this, and we'll see that in a minute. The other thing is computational, because you can derive these joint matrices, and you can throw these numerical methods for sparse matrices on these, and they are very, very, very efficient. So it's a very important thing that we're able to kind of have kind of model components that have sparse precision matrices. This slide here is my favorite slide ever. And sorry, it looks a bit innocent, but it's not. Okay, just to show you why working with precision matrices is the right thing to do, and why I don't care about covariance matrices so much. Okay, so here is a very simple hierarchical model. X is a different X from the other X. X is normal with some mean and some precision matrix. Okay, and then you add another layer where the X you had is the mean in the next layer. Okay, so you draw X from a normal, and then that X is a mean of the next. So Y given X is that. This is essentially that you're adding up two terms. If you then look at the joint distribution for X and Y, and work out what the precision matrix for X and Y is this very simple expression. Okay? The nice thing here is you see that if you start with a QX in the upper left corner, this is the model you had, and then you add another term, and you see you just expand the matrix. Okay? So you just add the contribution from the next layer in the hierarchy. Okay? And you see, okay, why is this important? There is no matrix multiplications. There is no matrix inverses. There is nothing. It's just every kind of new layer just adds a new kind of contribution to these precision matrices. Okay? If you have time to spare, try to work out this using covariance matrices and see how it goes. You know? And you see that it's a mess. And then you scale all these matrices up to some 10,000s, and you have to do all these calculations all the time, and you say that that root is dead. It doesn't work. So this is like plug and play thing with the precision matrices is so convenient, and this is one of the two main reasons why we just have to stick with precision matrices and not covariances. The other thing is computational, and essentially sparse matrices are, of course, much faster to compute with and than dense, of course. The special case here is what we all know as common recursions. Okay, all the kind of nice recursion results we have for dynamic linear models is a special case of something more general. Okay, and also this kind of thing is what's also kind of appear in the dynamic linear models. All these matrices are extended all the time, and you only change the kind of, you just add on. And so only change a few elements. So if you think that you have these kind of precision matrices and you can, what you want to do with them is essentially to factorize them. This is a Cholesky factorization. And you want to solve linear equations. Okay. You solve Qx, or you solve the Lx is B or L transpose is B. What we also need to do is to compute the diagonal of the inverse. Okay? And this is like a generalization of the common smoothing recursions. That is kind of valid for dynamic linear models, and you can do that in general. Okay. So it turns out that you can compute very efficiently also the diagonal of the inverse of a sparse matrix. And the timing you get for these kind of results is that if you think of matrices in, I say in time, think long and skinny ones. This is what you get in time series. The cost is order n, so the cost is linear. So it is the best you can do. It takes as much time to write out the solution than to compute it. And in space, if you think of kind of a lattice or structures in regular structures in space, the cost grows a little bit, so it's up to n 3/2. So you pay another square root of n. In space and time, you have a kind of a cube. Then the cost is like n square, and beyond that, it's growing slowly towards n cube. That is kind of the general result. So especially for time and space, and also space-time, if these models are not too large, this is very, very efficient. Okay. So what is the task? So this is the posterior density for what we define as a latent Gaussian model. X is the latent field, that is the prior is Gaussian. Theta is essentially all the parameters that are not Gaussian, variances, precisions, correlations, or dispersions, something else. Y is data, and so this is the posterior. So we have the prior for theta. Conditional on theta, we have something Gaussian. And this is, again, to remind ourselves, we don't define this from the beginning. This is a consequence of your model. Okay? So this Gaussian component. And then some of these components are observed. So what we want to do is kind of compute the posterior marginals for the latent field and also for all the hyperparameters. So this is kind of the task we want to do. And this is kind of, we don't want to kind of estimate just the mean or the mode. We want to compute the marginals, and from the marginal, we can compute the mean and other properties. Just show you how this kind of computation go in the Gaussian case, where we can kind of do exact calculations. And it's from there, it's kind of straightforward, essentially. So the whole idea is very easy. Okay. So we have looking at the pure Gaussian case. So we have some observation y that is a noisy observation from a smooth line. Smooth curve m at location I. And we have some noise with known precision, just to make things easy. And we assume that this kind of smooth curve is smooth with respect to I or time. Okay. So we can think of that, we have given these observations, and our code is on the left. And what we want to do is kind of smooth these kind of data. And you might think, oh, this is not very difficult. You can throw any kind of smoother to this and it works fine. Of course, the problem is not to solve this problem, but to show how the computation goes. So if you formulate the kind of the full model, we can start with that we have Gaussian observations. So yi is the observation at index I or time I. It's just you observe the curve at that point, and you just add with some noise. And the precision is kind of fixed. And then we need some model for a smooth curve. And then we use a kind of a spline model. And this is like an intrinsic model. So you see here the expression in the square is nothing else than the second derivative. So the second derivative of this curve squared. So this is like a cubic spline, stochastic cubic spline. Inside here, there is a parameter theta. This is a smoothing parameter, controlling how much we want to kind of smooth this curve. And this has the form as this is the hyperparameter. And to be kind of fully Bayesian, we put a prior on this smoothing parameter. Okay, so putting a prior is not as easy as it seems here, but just for the sake of argument, we just assign a gamma prior for this. Okay. So this is the model, and from this model here, and given the observation, we want to kind of more or less compute the marginals for the smooth curve and also the marginal for the smoothing parameter. Okay. What we have here, condition on the smoothing parameter, the spline and the data is jointly Gaussian. Okay, so the spline and the data itself is jointly Gaussian, and we don't have to work out the details, but it is. So simply we can use this simple identity here, saying that the marginal for the smoothing parameter given the data is simply proportional to the joint divided by the conditional. Okay, this is like statistic 0. Okay, so the joint distribution is Gaussian, and what's important with the Gaussian is that we can compute it. And then we have the prior, that is defined. If the joint of x or y is Gaussian, then also the conditional distribution for x given y is also Gaussian. Okay, we can compute it. More importantly, we also know the normalizing constant for that conditional distribution. Okay, so it means that we know this. We know the shape of this posterior marginal for the smoothing parameter exact. We don't know the kind of the normalizing constant. Okay. So what we can do to investigate this is that we can study the smoothing parameter is easier in log scale, so log theta. We can find the mode. We can locate the mode, and then we can kind of investigate what happened on the left-hand side, the right-hand side. We can lay out points. Based on the curvature information at the mode, we can get a feeling for the scale. And based on this, we can kind of lay out points. And since we know the shape exact, we can kind of draw this up. So we can compute the density in all these kind of points. And if we want the marginals, we can just do some kind of interpolation in log scale. And this is our kind of best guess of the posterior marginal for the smoothing parameter. Okay? So we don't need any kind of course, we don't need any kind of sampling to do this. The ratio between all these two dots is exact. The only thing that we have is kind of error is that we don't know the normalizing constant, so we have to compute the normalizing constant numerically from this kind of interpolated margin. A consequence of this is that we have computed the marginal likelihood or the evidence. This is just the normalizing constant for this that you need to make it integrate to 1. Okay? So that's a kind of byproduct of doing this. If you think about the posterior marginal for the spline itself, then the condition distribution is normal. So if we know the smoothing parameter, the distribution for the spline is normal. And then you can see that the marginal for the spline at any time point I is this conditional distribution that is normal. And you just have to integrate out the uncertainty in the smoothing parameter. Okay? That we have already computed. Okay? So you see that the marginal here is like an infinite mixture of normals. Okay? With the weights given by the posterior of the smoothing parameter. So what we can do, we can come back to all these points we have already evaluated this kind of density in. Because here we have to compute the condition distribution, and then essentially we have the marginal distributions. So for all these points here, you can kind of draw all the normal components at these points. So the true marginal is approximated by a mixture of those. And the weight is given by the posterior density of the corresponding smoothing parameter. Okay? So we know the weights in this mixture, and then you get this kind of mixture. And now you can, for every point in X space, you can kind of sum up vertically to get this kind of result. Okay, so this solid line here is kind of our guess for the posterior marginal for the spline itself. So it's just a kind of a mixture of these normals, where these weights are given by the posterior from the smoothing parameter. Okay. This is essentially the basic idea, and it's essentially this. Is just need to kind of extend it to different cases. So we need to tackle kind of more than one hyperparameter. We need to tackle non-Gaussian observations and a lot of practical complications. But it's like this is the main idea. Okay? And this kind of makes sense because for a lot of these latent Gaussian models, the dimension for the hyperparameter is small, while the dimension for the latent field can be very large. Okay? So doing this kind of separation very clearly between the hyperparameter and the latent field is a very nice thing to do. If you have more than one, let's say you have two, you want to kind of explore this posterior. And what you do is kind of you locate the mode, And when you're at the mode, you get the Hessian, and then you get you get the dependency by looking at the eigenvalues and eigenvectors of the Hessian matrix. And you can, from this, you can do layout points. And from this point, these are the points you can use for doing the integration. The integration that you integrate out the hyperparameters. For every of these integration points, we can then compute all the marginals for the latent field, and then we can simply mix all these together using a mixture. In the case where you have non-Gaussian observations, then we can look at what is there that is goes wrong, in the sense that where do we have to make an approximation. Okay, so the posterior marginal for the hyperparameters is still the same expression. So the joint distribution between the data and the latent field is non-Gaussian, but is known. This is the model setup. The prior for the hyperparameter is also known. And then we divide by the conditional distribution. And this turns out this is non-Gaussian and essentially unknown. And if something is unknown, it doesn't mean that we have to stop doing something, of course. And this community has been much better to pursue this than the stats one. So what you can do is that we can use a Gaussian approximation to the conditional distribution. And it's important that this approximation is indexed by theta. Okay, so if you change theta, you should have to compute a new approximation. Okay. And for the latent field, you can do exactly the same thing. For the spline, or for the latent field, you have the joint. You have, again, the notation is a bit messy, sorry. But again, you can compute a Gaussian approximation. This is indexed by both the value of x and theta. Okay, so this is the hard part to make this fast. Okay. So essentially what we're doing is using this very simple identity to compute marginals, and I find this much more intuitive and easy to understand than what you learn at school when you're doing the integration. Okay, so if you have a joint distribution x and z and you want to find the marginal of a z, the standard tool is to integrate out x. Okay, and mathematical equivalent thing is to divide by the conditional. Okay, it's the same thing. Okay. So essentially, this leads to, if you want to approximate marginals, you can approximate conditional distributions. Okay, so if you want to approximate the marginal for z, is proportional to joint divided by the conditional, and this is the same as integrating out x. Okay. When this conditional distribution, when you take it as a Gaussian one, this gives us what's called this gives us a classical Laplace approximation. Okay, and that was invented for doing integration. Okay, and this is as old as the name suggests, of course, and it's a very intuitive thing to do. Okay, so what you can do to compute all these modules, you can approximate the margin for the hyperparameters. For every value of the hyperparameter you're interested in that you lay out to do the integration, you can approximate all the marginal for the latent field. And then you can simply use these results. You can approximate the joint for the hyperparameter. From that one, you have to do some kind of interpolation and then integrate out to get the marginals. For the latent field, you have to integrate out all the hyperparameters. So this is essentially what you have to do. This is my second my second favorite slide. This just shows the structure of the Gaussian approximation. And you might think, okay, you have another Gaussian approximation, what's so special about this? It's like, by construction, this approximation is kind of, I wouldn't say well-defined, but it's kind of constructed to be accurate. Okay? So it has this form. It's minus 1/2 x transpose qx. This comes from the prior. Okay? And then you have a contribution that comes from the likelihood itself. Okay? And here we do that in log scale. So you sum up log of pi of y I given xi. So only some of these x's are observed. And then you see that if it wasn't for the likelihood, then this conditional distribution is Gaussian. If the log likelihood is quadratic in x, essentially it's a Gaussian, then this is conditional distribution is again a Gaussian, and you can compute this exact. The only kind of error you do is that if you approximate the likelihood, the log likelihood with something Gaussian, okay? So you can do that iteratively, of course, and you can construct a Gaussian approximation at the mode. The nice thing here, it's two things, is that you see that the contribution from the likelihood only enters in the term the diagonal of Ci. Okay? So it's only entering on the diagonal of the matrix. Okay? It means that it essentially means that the way the data influence this conditional distribution is to alter the marginal distributions, but all the interaction terms that has interaction between xi and xj comes from the prior alone. Okay, so it's like all the interaction, how they are dependent, they come from the prior, that is Gaussian, but the marginals is shifted by the data and could be slightly off Gaussian. Okay, so that's where you make the error, and not in the dependence itself. This is very roughly. The other thing is that the Markov properties is preserved. So if you don't have any data, you can do computation very quick. If you condition on data, you can do computation as quick as before. Because the zero pattern of Q is the same with data or without data. So this is a very nice property. Just to kind of remind yourself what is the kind of the classical Laplace approximation. And this is like computing approximation to that integral over n times a function g, where n is a parameter that essentially goes to infinity. And what you do to get this, and this is a natural thing, anyone in this room would have done the same thing. This G must have a kind of have a mode. So you just expand around the mode to second order. Here assume that the mode is 0. The derivative is 0 because you have the mode. And then you know the normalizing constant for a standard normal. And that's it. And that's the approximation. And of course, when this kind of integrand gets more and more peaked, this is more and more accurate. The nice thing, and this is truly this is what kind of makes a difference, is that if you do the error analysis here, you get that the estimate as a function of n divided by the true value is 1 plus order 1 over n. Okay? The first thing is that we have a relative error instead of an additive error. Okay? So if the true value is small, your estimate is small, so you're kind of 1% off, no matter the size of the integral itself. If you compare this to kind of sampling-based method that has additive error, okay? So if you try to estimate a small probability, that could be much, much harder to do when doing sampling, okay? The other is for sampling-based method that the error is order 1 of square root of n. Okay. where n is the number of samples. So relative error is a very, very nice property. And also you have this amazing rate. Okay. Of course, you can do this multivariate. Of course, you have just straightforward. And okay, I'll just show you a small example. This is a binary classification using a Gaussian prior, and we just have two observations. So you have the prior is dimension x is dimension 2 with the correlation 0.8, and you have binary observations. You observe -1, and this is this likelihood. And what we want to do is to approximate the marginal for x1. Okay. Then we can use these tools to compute the approximation. The solid line is the truth, and the dotted line is what you get if you to this distribution here just fit one normal, and from that normal you compute the marginal for x1. Okay, this is the easiest thing you can do. Okay, so you see you already here a bit off. So what happened when you use this classical Laplace is that for every value of x1, I have to compute a normal approximation for x2. Okay, for every value of x1, so I compute a whole sequence of normal approximations. And if you do that, what you get is something very close. Okay. So the whole a part of the message here is that if you can use a sequence of these normal approximations, and if you do that, you can achieve something that's really, really good. Okay. So why is it so? And this is a old result from '86 when these techniques was modern before the MCMC came around. So it turns out that if you have some parameter theta and you have repeated measurements of these, okay, so independent repeated measurements, then if you compute the marginals using this technique, then the relative error is n to minus 3/2. So it's n squared 1 over n times square root of n. Okay, after renormalization. So if you make sure that your approximation all the time integrates to 1, which you can, then you can achieve this amazing rate. Okay. And to have a relative error of order n to minus 3/2 is just stunning. This is amazing. And you also have this relative error. This is so nice property, and this is what makes all this work. And the error rate is, of course, is impressive. This is so amazing. It's very unfortunate that the assumptions for these results doesn't hold. It doesn't hold. It's usually not valid. It's like only for very simple toy example, this is valid. Okay. The main thing about if you have models where the number of data observations grow, usually also for every data point you usually have some random effect. So you mean that the dimension of the latent field is not constant. It also grows with n, and this destroys all the asymptotics, all the math. But the result is still useful in the sense that if you go back to this very simple example, you might see, okay, we have two latent variables. They're correlated with correlation coefficient 0.8. So they are close, okay? So they are similar. So they are similar in the sense that you can almost think of that you have one variable that is observed twice, okay? Because the latent field is smooth by construction, okay? And that smoothness gives you these replications, even though you cannot define precisely what the number of replications are, okay? So essentially that the effective dimension in the prior is much less than the mathematical dimension. So what I want to do now is to kind of discuss a bit the kind of background for having for doing fast computations on sparse matrices. It's kind of things that is cool to know, and the good thing is that we just have to use this kind of method. Gauss mark-around fields is very important in this setting because we said before that as long as you have components that have this kind of property, then you can easily add up and build the joint distribution. And the other thing is that you have this huge computational benefit, and also kind of memory issues is much less. So you use much less memory. And we come back to later that sometimes the model itself is have not this kind of property, but it might be able to rewrite a representation or approximation of that in that form. So what is a Gauss mark-around field? It seems it's a very fancy name, but it's just a Gaussian random variable that has condition independence properties. Think about this as like a Gaussian graphical model. And you know which one, xi and xj, that are condition independent. Okay. So if you have a set of conditional independent, you know which one that is condition independent. You need to constrain the parameterization to achieve these properties. And again, covariance is difficult and precision is easy. And it turns out that, yeah, you know this result, but conditional independence gives zeros in the precision matrix. Okay. And this is like the one-line proof of this. This is easy. So you have this density here. Also here you see this. It's kind of simpler to write the normal using the precision matrix. There is no inverse. Okay. So Qx transpose Qx. It's just a vector matrix vector product. And Q is sparse, so it's very quick to compute. So if you have a lot of conditional independence, you have a lot of zeros. Okay. And this is kind of beneficial when doing the numerics. And just remind ourselves about what we all know about the Cholesky factorization, just to kind of set the scene, because we know we need that later. Okay. So if you have a symmetric positive definite matrix, you can factorize it in L transpose. L is low triangular. This is the Cholesky triangle. And this costs about n cube flops. And if you have that, you can solve equations. Ax is b, or so many right-hand sides. If the right-hand side is identity, this is how you compute the inverse. Okay. And so this is what you do. So if you're solving Ax is b, where A is positive definite, you do the factorization, you do this forward substitution, you do forward, and then you do backward, okay, to do the solving. And we've seen this before, this kind of forward and backward. Is all these kind of recursion algorithms. All these kind of recursion algorithms, you have this forward and backward. And if you work out the case, if you have exact recursion for hidden Markov chains, if you write them up in the Gaussian case, this is exactly these equations. Okay. So solving this the linear system is the same as computing the mode. Okay. We can use this to sample a Gauss mark-around field, to sample from a normal where we know the precision matrix. Okay. If you then do the selective factorization of Q, and you solve this L transpose X is set, the right-hand side is random noise, then the solution of that linear system has the correct distribution. Okay, so this is just working out what the covariance is, and you get the correct result. Okay, so this is how we can kind of generate a sample. It turns out that in order to understand how this numerical algorithm for sparse matrices works, we need to understand what L means. Okay, so we need to understand what does the Cholesky factorization, the Cholesky triangle of the precision matrix mean. Okay, what is imputation? And the answer for that gives you these kind of cool results. Okay, so if you factorize Q into L transpose, and then you solve this equation, then you get something that's a correct distribution. And this is like solving it from backwards and forwards. Okay. So it means that if we write out the last equation, that is ln xn is set n, and you solve that, you get this expression for x. And then you see that the mean of xn is 0, and the variance of xn is 1 over ln n squared. Okay, so it means that the precision for the last element is ln n squared. Okay. If you then go to the next one for xn minus 1, and you see that this is conditional on the previous one for xn, because we're solving this from backwards and forwards. And you see that the variance come from the noise term is set. So the conditional precision is this diagonal term squared again. And the off-diagonal terms relate to the conditional mean. Okay? So you have ln n minus 1 xn. Xn is fixed. So that comes in. It's only give a contribution to the mean because it's kind of fixed. Okay. And then you can work. You can do the same thing, and you get kind of this very nice interpretation that the interpretation of the Cholesky triangle of the precision matrix has this interpretation. Essentially, the expected value of xi, conditional on those with a higher index, okay, has its form is minus 1 over lii, and the contribution is lji for xj. Okay. And the precision for xi, given those with a higher index, is lii squared. Okay. So this gives us the interpretation of this Cholesky triangle. The next thing comes if we know something about the conditional independence here for this set, for this xi and those with a higher index, if I know that xi and xj are conditionally independent, given all those that are higher than I, then this lji must be 0. Okay? So if I know something that is conditionally independent, then that variable cannot contribute to the other one, and the only way it has to be is that lji must be 0. And zeros here is our friend, because if you know that something is 0, you don't need to compute it. Okay. So essentially, you can define what's called what can be called the future of I. The future of I is I. Future of I except j is all the indexes higher than I, but not j. Okay. So then you have this result saying that if you have conditional independence giving the future, then this lji must be 0, and you have an equivalence. And this is essentially the whole trick, is that if we can verify up front that lji is 0, then we don't need to compute it. Okay? And the way to verify this is saying that xi and xj is conditionally independent, giving this future. Okay. This result is too strong, and then this is an equivalence. So it turns out that the easiest way to check if xi and xj is independent is to compute L to check if that term is 0. Okay, so that trick doesn't work. So we need something more, have a kind of weaker condition that it's kind of we can check more easily. And to do this, we can make use of the global marker property. Okay, the global marker property is simply if this is the kind of conditional independence graph, and you have sets A, B, and C, and the set C separates set A and B. Then XA and XB, conditional XC, they are conditional independent. Okay, so you have this kind of property, and all this kind of Markov properties is equivalent in the Gaussian case. Okay, so if you fix the gray ones, then the black and whites are conditional independent. Okay. This is a very nice property, and we can do this for. We can use this global mark property to provide a very simple and sufficient criteria for checking these things. So simply, if this future set separates I and j, then this term must be 0. Okay, so that's the whole trick. And this is numerics for sparse matrices. This is that trick. Okay, so if the future of I separates I and j, then this term is 0. Okay, we do an example to see how it goes. And the corollary is if you have two neighbors are not separated, so that term is always 0. So the whole trick is that you can use the global marker property to check these terms, and you only compute the terms that is not known to be 0. And that's the whole savings. Okay. So here is the easiest non-trivial example. It's a very simple graph, 1, 2, 3, 4. And if you then fill in the precision matrix, you have connection, non-zero terms between the elements 1, 2, 2, 3, no, 1, 2, 1, 3, and 3, 4, and 2, 4. Okay. And the Cholesky triangle, it's on the right. So all neighbors are never separated. So two neighbors are L kind of inherit the non-zero pattern from Q, the lower triangle part. There will be additional kind of fill-ins, and there are only kind of two places that are in question. So we can check the first one. This is element, let's say, 4, 1. Okay. So if you look at the element 4, 1, so we take node 1 and 4, and we condition on all those with a higher index. This is 2 and 3. And you see that 1 and 4 is separated by 2 and 3. Okay. So it means that that element 4, 1 must be 0. Okay. The other element is 3, 2. So if you take the nodes 3 and 2, we condition on those with a higher index, and this is 4. And you see, I cannot point, you know. So 2 and 3, condition on 4, you see that, but 2 and 3 are connected through 1. Okay, so they are not separated. Okay, so it means that essentially the term 3, 2 can be 0 and cannot be 0. It's in general non-zero. Okay, but the term 4, 1 is always 0. Okay? And if you know this, then you don't need to compute that term. So simply you're doing the Cholesky factorization. You're just skipping over all the terms that is known to be 0. And that's how this algorithm works. So it's very easy. This is example. This is autoregressive process. This is the precision matrix. Since it only depends on one neighbors, you only have connections there. So the precision matrix is just tridiagonal. And then you see, then you can check which kind of terms in L do we need to compute. And since neighbors are in general non-zero, so we need at least to compute these terms in L. And all the terms, if you do the kind of similar check, you find out that all the other terms in this L matrix is known to be 0. Okay? And of course, this holds in general. So if you have a band matrix, you can factorize, this is Cholesky factorization, is a band matrix with the same bandwidth. Okay? So this kind of holds in general. And this is one of the reasons why these autoregressive processes are so efficient, because they're kind of optimal in the sense they don't have any kind of fill-ins. Okay. And it's kind of very easy to write code because it's you just modify the loops to go between the diagonal and the bandwidth itself. Okay. The other kind of trick in the bag, what these numerics do, is to do a reordering things. Since we have a band matrix, it might be able to kind of take any kind of sparse matrix and kind of reorder, relabeling to give it a different ordering, so it's kind of the matrix gets close to a band matrix. Sometimes it is possible, and of course you can permute the vertex. So if you do that, you can just rearrange the terms, and you can compute the factorization there. You can solve equations, and you can just permute back when you're done. Okay, so this is what you can do. So let's say you have a model like this. This is just the graph of Germany. So this model is kind of constructed in the sense that two neighbors regions are neighbors. Okay. So you have this is the map, and this is the graph of the Gauss-Markov field on the right. What you can do, you can kind of the numbering of this node is kind of rather not random. It doesn't follow any kind of particular pattern. What you can do, you can start in the one corner and kind of go like you pretend to go like row-wise or column-wise, just like it was a kind of a square image or a matrix. And you can kind of define ordering of the vertices like this. So the picture on the right shows the kind of ordering, and the other one is just a subset of this. If you do this, you can kind of take the matrix on the left and just convert it to a kind of band matrix on the right. And you see that you can do this. And what you can do the factorization on the band matrix itself, and you can do you can solve equations, you can do everything there. And when you're done, you can permute the solution back to kind of reorganize indexes. Okay. So that's a kind of a common trick. But this kind of band thing is kind of doesn't really apply to any kind of useful thing except very simple time series models. So what we need is something more general. And this kind of trick here that kind of shows what's going on. Suppose we have a graph like this. So we have a node 1 in the center, and then from 1 we have a lot of kind of condition independent nodes. Okay, and then you have the first, the middle column is a precision matrix, and the right column is a Cholesky factorization. If you then check these hatches, you see that if I check if we need to compute element 4, 3 in the matrix, I take the two nodes 4 and 3, I condition on those with a higher index. This is 5 and 6, and check if 4 and 3 are separated, and they are not, because they all depend on this node number 1. Okay, so they are not separated. If I check, do I need to compute element 4, 2? I take up this node 4 and 2. I condition on those with a higher index. Is 5 and 6, and you see 4 and 2 are still connected through 1. Okay, so you don't get any kind of condition independence here. Okay, because all are connected through this node 1, that is kind of a modern node, and it has a low index. So essentially, there is nothing to be gained here. You have to compute the whole matrix. Okay, things change very rapidly if we just swap node 1 and 6. Okay, so we place the node that has a high index in the center, and all the others around. Okay, because if I now check node 4 and 5, do I need to compute element 5, 4 in the triangle? Then I take 4 and 5, I condition on those with a higher index. This is 6, and you see that 5 and 4 is separated by 6. Okay, so it means that that corresponding element is known to be 0. So simply that just swapping these two elements, you see that you just rearrange the kind of the precision matrix. This is the middle column. And the triangle on the right, you see there has no kind of fill-ins at all. Okay? So that's very, very, very sparse. So this is kind of, you can compute this in linear time. Okay? So you have this dramatic change by just swapping kind of two nodes. Just relabeling them. Okay? And this kind of gives rise to something called nested dissected reordering. So you have your big graph. You simply select a small subset. You condition on that. If you do that, you kind of separate your graph into two independent graphs. And then you continue recursively. Okay. And if you do that, you kind of obtain this optimal rate for factorizations. This is in the spatial case. So here is the same kind of graph. So you can you have the black line. You kind of divide this in south, west, and northeast, and then you kind of separate each part again. And you can do that again and again. You do this kind of recursively. And what you get is that you reorder the matrices into these kind of forms. Okay, and this is more or less the most efficient thing you can do for these kind of things. And this is the corresponding Cholesky triangle. Okay. Of course, there are different forms of reordering algorithms that is kind of in between this, and usually they are very, very quick. And we don't need to kind of compute any kind of optimal reordering. It's like any decent one will do, you know. And sometimes you can compute several and check which is best for your problem, and you can go on from there. So essentially, how does it work? Essentially, we just use existing software. They're all kind of implemented in R. MATLAB has better support, but also R is kind of catching up on these kind of issues. Okay. I think I want to also mention how to compute the diagonal of the inverse of a sparse matrix. Okay, we skip the details, just giving the main result, and then we go on. This is so cool because this is a result if you download a library for sparse matrices from the numerics community. These kind of algorithms is typically not included because they are interested in solving equations. Okay, this is something else. I know of one library, this Sholmo, that is now default in MATLAB, that has a version for the non-symmetric case. Okay, and this is the only one that I know. And otherwise, it's quite easy to code itself if you know the internal data structures. You know. This result is kind of generalizations of recursion for common smoothing. Okay, so it's formal forward filtering, backward smoothing things. Okay, and this was I just showed. This is a copy. This kind of algorithm was this result was found in this paper from '73 in the Power Industry Computer Application Conference. Okay, by these Japanese, I think Japanese guys. Okay, so I have a copy of the paper. It's quite fun to read. This is old one, and this is a beautiful result. But we can kind of understand it more easily using conditional independence. So we can have this we have this result that showed that if you solve L transpose X is set, we get the sample, and this is essentially what is going on. So this provides a way of sampling, defining a kind of non-homogeneous autoregressive process backward in time. Okay. What you can do, you can multiply by xj and take expectations, and you get equations like this that connects the covariance sigma ij with other covariance sigma kj through this L. Okay. And okay, these are technical details, and Okay, here is the result. This equation connects sigma ij with sigma kj. So we kind of define recursions. And we don't need to compute all if we're only interested in the diagonal terms. And it turns out, this result is a beautiful result. You say that only those elements in L that you have computed, you need to compute the covariances for. Okay? Only those elements. If you compute the covariances for only those elements in L that you already have computed, then you can compute the margin variances. Okay? And this is exactly the same result you have for Kalman recursions. And this result only depends on the graph. It doesn't depend on the values of the matrix. So you can do all this check. You can do this without knowing the values. Okay. Okay. So this is, okay, it's complicated. Okay, but you have these kind of results. The main thing is that you can compute the inverse of a diagonal matrix, of a sparse matrix, sorry. If you have the Cholesky factorization, it's all about doing another calculations using the Cholesky triangle. Okay. So a little bit about R. So you have also this web page, INLA.org, that kind of hosts the whole code to do all these kind of things. So it's a complete R interface to do this computation with INLA. You can build models, you can do all the analysis there, and so on. Okay. Just show you a very, very simple example. This is just a toy example. This is just, again, smoothing time series, binary, not binary, but binomial data. So this is a sequence of 0 and 1s and 2. So this is like one of these kind of stupid examples. It's a number of days it has been raining in Tokyo for 2 consecutive years in '83 and '84, something like this. So this is the data. And what you can do is you can simply smooth them. You define a kind of a spline on the circle, because what happened at the end of December is same as happening in early January. Okay. So this kind of defines the model using this standard kind of R syntax for how you define the model. I add a little extra to show how to use this kind of new kind of priors that we are kind of also working on, this penalized complexity priors that really kind of, using that we can kind of define this priors and know what we're doing. Okay. Okay. So you simply define the model, you can run your result on this data set, the family is binomial and so on. And this is just 1/3 of a second, more or less. You can compute all the modules that you would like to do. Okay. And what you get is these kind of fitted values. So these are the kind of the posterior maps of the posterior distributions, the quantiles, the medians, the mean, for the probabilities for having rain at that specific days. Okay. I just list some very non-standard features that we have added that really kind of expand the class of models. You can define using the standard formula specification in R. Okay, and they are, without them, we need them. You know, something on replicate and group is that if you have a time series model, that's a function of time, but for every person has a different replications of that time series. Okay, this is happening if you have time-dependent probability, or you might have other cases as well. You can define what's called a replication. So internally, this kind of replicate the model, constructing independent copies of that model, and we could just do that very, very easily. You can easily set up the code to have more than one family. You can have mixed Gaussian response, Poisson response, binomial, do all these kind of things. Very easily, you can have many different responses. You can copy terms, and that's a very useful feature. Instead of having just for linear predictor, you have one contribution from one model. You can have another contribution for the same model twice. So you can copy terms. You can have another layer in the linear predictor. You can do the computation somewhere else, and there is a nice collection of very useful features. Okay, I speed up a little bit these kind of more technical things because I want to come to this point, this kind of section. This is more Gaussian fields. So this is back to the setting is that having Gaussian components that is a Gauss Markov random field or has its Markov property is very, very valuable. And if you don't have that, all the computations are very difficult. It's not that difficult. That takes too much time, there's too much memory, and so on. And one kind of particular case is the Gaussian fields, okay? And we think especially in dimension 2. So, and usually Gaussian fields are defined using covariance functions. Okay, they only depend on distance, and especially this Matern family is kind of popular and useful. This gives a very, not a very dense. The covariance matrix is dense, but you know all the marginals. There is no boundary issues. It kind of resolution consistent, but it kind of takes a bit of time. This is cubic computational complexity. It has severe difficulties if you want the non-stationary version. This is not easy to do working with covariance functions. And also curved spaces. If you want to put Gaussian fields on top of a sphere or deformed sphere, then it gets more difficult. And then we had talked about these Gauss Markov random fields. And if you want to know more, there is a useful book over here about them. And the key thing for Gauss Markov random fields is that they're very fast to compute with. So all the conditional distributions, it only depends on the neighbors. So it's a very simple conditional interpretations, very little memory, very fast computations. But they come, of course, with some benefit and some drawbacks. And one is conditional modeling, is that you can kind of define models by defining conditional distributions. But then, in a way, you can define conditional properties, yeah, but you have no control of the marginals. Okay. But the strongest argument is essentially the computational speed. If you can take a model and kind of make it Markov, then you can gain a lot computationally. And that's the nice things. The downside is not easy to specify this Gauss Markov field to get what you want. And that's why you often see this. It's even they are kind of implicitly defined like these autoregressive processes. Some of these are kind of just smoothing priors. They say that it's a spline model, say it's priors that smooth that my value is similar to my neighbors. These kind of constructions that so there's a link from the conditional distribution to the covariance to the margin properties is very complicated. So this is like having a big matrix and kind of guessing what the inverse is. This is annoying. It turns out that you can mix these two things in the upon case of when you have a Matern covariance function. Okay, and these turn out to be. There is a nice connection in a too nice paper by Peter Whittle. This is like going back to the mid-50s, saying that the solution of this stochastic partial differential equation is a Gaussian field with a Matern covariance function. Okay, and this kappa here is a constant, and then you have the Laplacian, and then you have the right-hand side is a spatial Gaussian white noise. Okay. It turns out that if we can work with this kind of object here and its extension, this stochastic partial differential equation, then it turns out that you can easily define Gaussian fields on curved surfaces. You can easily do non-stationary variance. And you get Markov properties more or less for free. Okay? So all the computation properties are excellent for these kind of, when you work with these kind of models, if you do it kind of correct. And it turns out that we can make kind of use of this finite element methods. It's kind of standard tool in numerics. And you can do this to construct a numerical representation of a solution. You can write continuous, you can have your Gaussian fields in continuum by using basis functions. And basis function you can use on 10 functions, and you simply build up the solution by using linear combinations. Okay. And it turns out you can take the continuous Gaussian field and you can kind of project it down to this kind of basis and kind of say what kind of distribution for the weights gives me the best kind of projection. And it turns out that you can construct the joint distribution for the weights can be constructed so it's Markov. And you can construct at no cost, you can do the math, you can write down what the precision matrix is at no cost. Okay? So it means that we have a connection between the Gaussian field, where you know the margin properties, you know the covariance functions because it's monotone, and a Gauss-Markov random field constructed on a triangulation of the space. And think it's here. So in a way, you can think of, here is some area, we have some data. We can throw in a regular lattice, and you can do a different form for triangulations, and you can define these Gaussian fields on any of these kind of triangulations, and they all correspond to the best representation of the same reference. Okay? So you can do this kind of consistently. So it means that instead of working with a lattice, we can work with a triangulation and much fewer kind of the weights, so it's much faster. Additionally, you have this Markov property, so all the matrices here are very, very sparse. So you can do this, all this, using this, you can do kind of these kind of models very, very efficiently. You can also throw this SPD on the manifold. You can throw this on a sphere, of course. You can just drive it with a Gaussian noise on the sphere, and you can have a triangulation of the sphere. Or you can throw it on some other kind of non-regular sphere. And the only thing that changed is that in order to compute these kind of matrices, you need a kind of inner product between basis functions. And here you just do the inner product over the surface. So it's very, very, very easy. And you can go beyond here. So this is like, you can go beyond kind of classical Matern models. So you can have standard samples. You can, instead of driving these SPDs with Gaussian noise, you can drive it with complex Gaussian noise, and you can look at the real part of the solution, and then you can generate oscillating fields. Okay? You can also rotate them to have them anisotropic. You can make them really, really funny by making this kind of parameters depends on where we are, and this is kind of the key thing to define non-stationary fields, that you can make the parameters that defines the SPD depends on the location. Okay? And still, you have the same computational properties, and you can write down the Markov solution. You can throw this on the sphere. You can have two of those. You can have oscillating fields on the sphere. You can drive it with another external force. You can generate covariance function that goes around the sphere, but it's still Markov. So the conditional distribution only depends on the small neighborhood around this. And still you can achieve these kind of results. And you can have fancy realizations on the sphere. You can have bivariate versions of this. You can have one, the left is kind of a Matern function, and it can be a multivariate version of this, where the other part is oscillating. And one example where you need kind of one smooth and one oscillating field is one, if you want to do interpolation of temperature and pressure, like so on the sphere. Temperature is smooth, pressure is oscillating. If it's nice weather here, it's bad weather somewhere else. Okay, so you have these kind of oscillating things. And you can do this, you can have one field that is smooth, the other one is oscillating, and still they are kind of defined jointly for this system of SPDs. Okay, you can do this. Another nice example, if you are doing modeling of rain, this is just to show you an example where you can do this non-stationarity. And rain in Norway is not flat, it's a lot of mountains, so the rain depends on the topography, the height, and so on. And in a way, you can essentially feed the geometry of the Norway and use that as covariate for driving these SPDs. Okay, so you can use a gradient and elevation, and you can kind of estimate the effect. You can use this to define implicitly the non-stationarity. Okay, then you can get correlation functions like this. In the west part of Norway, it's kind of different from the east part of Norway. And so you kind of use these kind of physical constraints or physical covariates to kind of define implicitly covariance functions. Okay. Okay, so I come to the end. And just say this kind of latent Gaussian models is kind of everywhere, and it's important to solve this class model well, and essentially we can. And as I said, this class of latent Gaussian model is very convenient computationally. It doesn't help you with doing the modeling itself. So if you have a model, you can cast it into that, and you have some general kind of code, and that can do the inference for you. It's so important that every kind of component in these models goes marked around fields. So if you start with something sparse, you're adding up something sparse, and everything is sparse, everything is fine. As soon as you add things that is component that is large, it's working with covariance matrices and so on. Things get very, very difficult. And it's possible often to kind of rewrite models in this form, and you saw this. And most of the models you will use can be, you can use this Gauss mark around fields. Yeah. And these kind of algorithms for these models works great in near all cases. Even if you can kind of construct cases where it's not working so great, the results are still good. You know? So it doesn't kind of really crash. There is, of course, a potential to improve the results in some way without much cost. I'm not going to discuss that. I just want to mention that there is also, there was a poster, I think, yesterday about latent Gaussian model for topic modeling by who and all. They kind of reuse a lot of, many of these ideas to kind of provide a quite nice solution to these topic models using these Gaussian models. Okay. Here are some main references. There is this web page that INLA.org that hosts all the code, everything. It's all there, and there are some key references. Okay. I think that I end my talk here.
Okay, let's thank the speaker.
Hi, this talk is very inspiring everywhere. So I was wondering, you talked about when you're doing Laplace approximation, it works best if you have relatively more sample than like nodes in the network. So then I wonder, does that correspond to sparsity of the network, or does it correspond to low rank of the precision matrix or low rank of the covariance matrix? How can I take advantage of this?
Okay, I guess we're back to this slide here.
Yeah, around here.
Yeah, yeah. So what these kind of results say that if you have kind of independent, if you have replicated, if you have a model with parameters theta and you have replicated observations of that, you're gonna compute these asymptotic results. And what I say that this is not kind of valid because you never have kind of replications. And if you have often, for every new data point, you usually have another kind of realization of a random effect. So you mean that the dimension of theta is also a function of n. Okay, so it means that all this kind of, this result doesn't hold. But still, I said it's kind of useful because you have very often kind of smoothing that kind of emulates replication.
Yeah. So, but I remember just a few slides later, you have a precision matrix that has 1 on the diagonal, 0.8 on the off diagonal, right there.
Yes. So it's like if the correlation here goes to 1, then x1 and x2 are the same.
Yeah.
So then it's more or less the same that saying that you have 2 observations and 1 variable.
Yeah.
Okay. So that kind of, even though the mathematical dimension is 2, you have in effect only 1 variable. So then you have a replication of n equal 2 in this case.
Yeah. How to achieve that in a graph?
This is something you don't achieve it. Either you have it or not. So it's like it's not something you can tune. It's something you have. But as soon as you have some kind of smoothing, you have this. You have an intercept. This creates smoothness. You have a spline model. This creates smoothness again. Like the observations between two neighbor locations are almost the same. Yeah.
What if that is the precision matrix Q? That was my question. What is that the center thing is the precision matrix?
Oh, so what is the inverse of that matrix?
No, so imagine that center thing is the precision matrix. Then how do I know that I have this property?
You have this property if you have smoothing components in your model. So like spline models and other things that do smoothing. Yeah. Then you get this. It is you cannot look at this from the matrix point of view. This is coming from the model itself.
Thank you.
Okay, we can discuss this more later.
Thank you for the talk. I have a question that is there any option of applying this method in the case where the latent distribution is a mixture?
Okay.
Could be like multimode like distribution. No,
okay. So then we're back to this slide, and so what happens if x is not normal but is a mixture of 2? Or several, and then this whole kind of system breaks down. Yeah? So the kind of the fundamental assumption doesn't apply. So then you're on your own. You know? No, so mixtures we cannot do. Mixtures are difficult.